Hello, welcome back to the second part of our lecture. Today we are talking about vectors. Vectors are probably the smallest building block upon which linear algebra is built. So this is very important that you are very clear on the concepts of vectors. So that's what we are gonna do today. Let's begin. The first question obviously is, what exactly is a vector? Now, if you ask a physicist, he will give you the answer that you are probably more familiar with. A vector is something that has both a magnitude and some sort of direction. So if something is 5 meters long, this is not a vector because all we have so far is the magnitude. If we add a direction to it, say this is not only 5 meters long, it's towards the northeast direction. So along with the magnitude and direction, now we have a vector at our hand. So we are familiar with this definition, and one very important thing about a vector is, as long as the direction and the magnitude is the same, it doesn't matter where the vector is, right? So a vector can start from anywhere as long as it goes at the same direction, the same length is the same vector. Now, if you ask a computer scientist the same question, so what exactly is a vector, he will probably give you the answer that a vector is just a list of numbers, an ordered list of numbers. The order is important. Now, for example, let's say we have a computer here with a RAM of 32 GB and 2 TB hard disk and graphics card of 8 GB. Right, so if we can express these informations in a list, so the vector would be something like this. Now the order is important. In this vector we have everything in gigabytes, so we have 32 GB of RAM. The first number determines how much RAM a computer has. The second number determines how much hard disk memory a computer has in gigabyte, and the third number decides how much graphics card memory the computer has. Now this is not the same as this one. So the order is important because the second vector, this one, it means we have a computer with 8 GB hard drive and 2048 GB of graphics card. So this is not the same thing as the vector we are talking about earlier. So this is not the same as this one. Now, not necessarily these two perspectives are talking about two very different things. They are basically saying the same thing. It's just two different perspectives. So if we can match this, we'll get a bigger picture, a more complete picture. When we think of a vector from the physics perspective, so something with a magnitude and a direction, we can always express it using a set of numbers or a list of numbers. For example, this vector can be expressed as a list of 6 and 3, the Cartesian coordinate of this vector, right? Now, similarly, we can map every vector in a two-dimensional coordinate system using two numbers. So every vector from the physics perspective has a representation as a list of numbers which we associated with the computer science perspective. Similarly, we can express a three-dimensional vector using three numbers. So here you can see we have the x and y and z coordinate. From the other end, if we have a list of number as vectors, we can always think of the geometric representation of this, which corresponds to a magnitude and a direction. So this is how we can go back and forth between the two perspectives. And of course, this is not only limited to two dimension, because if we have a list of three numbers, we can always show it in a three-dimensional space. Now, we can also have dimension higher than this, and we can also, in theory, express it using an arrow and a direction in a four-dimensional space. So one axis will correspond to this number, one axis will correspond to this number, and two other axes will correspond to these two numbers. But obviously, as we are three-dimensional creatures, we cannot think beyond three dimension, or we cannot graph more than three dimension. But in theory, this is possible. So a vector can be any dimensional, and it will have a representation as a list of numbers, and will also have a geometric representation that deals with a certain magnitude and a certain direction. Now let's see what we can do using these vectors. The most basic vector operation is going to be, of course, the vector addition. So let's say we have two vectors, the green one and the red one, and we want to add them. How we add a vector is we start from the tail of the first vector, go along the direction of the first vector, end up at the tip of the first vector. After that, we go along the direction of the second vector, end up at the tip of the second vector, and the overall effect or the addition or the resultant vector is going to be the vector that goes from the tail of the first vector to the tip of the second vector. I'm sure you're already very familiar with this concept, so we don't really need to go very deep. And from this you can see that if we add vector A with vector B, this is basically the same as adding vector B with vector A. Now we can also think of the addition of vectors without thinking of an arrow and a direction and a magnitude. Let's think of the concept of a list of numbers. So let's say we have a vector that corresponds to the specification of a certain laptop. Now we have another vector that corresponds to the specification of another laptop. So this one has 16 GB RAM, 1 TB hard disk, and 4 GB of GPU. So if we add them, what we get is the combined specification of these two laptops. So we have total 48 GB of RAM in these two laptops and total 3 TB of hard disk and 12 GB of graphics card memory. The second vector operation is vector multiplication with a real number, and this is equally important. We have a vector and we are going to multiply it with a real number. In this case, the real number is 1.5. What we are doing here is we are multiplying 1.5 with every component of the vector, and as a result we are actually multiplying the length of the vector by a factor of 1.5. Now, as 1.5 is a positive real number, the direction did not change, but when we multiply the vector with a negative number, what happens is the length is multiplied by a factor of 2. At the same time, because of the minus sign, our direction of the vector has been inverted. Now, this operation, this multiplication, is called scaling, because here we are actually scaling the vector by a factor, and these factors, these real numbers, are what we call scalars. Now there is something interesting we can notice here. Now look at this vector, the vector that we originally started with, the vector 3, 4. If we scale it using all possible scalars, which means if we multiply this vector using all possible real numbers, what are the vectors that we are going to get? Here we have got 2, 4.5, 6, and minus 6, minus 8. But these are just two examples. If we take all possible scalars, we are going to get all possible scaled vectors, and all those vectors are going to sit on this straight line. This line is what we call the span of this vector 3 and 4. But we are going to talk about span in much more details in the future, so don't bother yourself too much with it now. Now let's talk about the magnitude of a vector. The magnitude is basically the length of the vector. So if we have a vector that is, let's say, 2, 3, and 5, the magnitude of the vector is given by the equation square root of 2 square plus 3 square plus 5 square. More generally speaking, if we have a vector of n components, the magnitude of that vector is going to be square root over the squared summation of each components. There is another formula that gives us the magnitude of a vector, and that is this one, the square root of the dot product of the vector with itself. Well, that's cool, but what exactly is a dot product? Let's look at that. Let's say we have two vectors. One has 3 components, v1, v2, v3. The other has 3 other components, u1, u2, and u3. The dot product is given by this formula. We are going to multiply the corresponding components of the two vectors and then sum them up together. So we have v1 into u1 plus v2 into u2 plus v3 into u3. If v1, v2, v3 and u1, u2, u3 are real numbers, then this multiplication and summation is going to give us a real number as output. Now, as we saw earlier, if we do the dot product of a vector with itself, we just end up with the squared summation of its components, which is exactly the square of the magnitude, or as we might call it, the norm of the vector. Now there is another formula for dot product, which is this one. The dot product of two vectors is the multiplication of the magnitude of those two vectors into cos theta. Here, theta is the angle between two vectors. Now we can get a few interesting things out of this equation. Let's say we have v and u. So the dot product between them is the multiplication of their individual lengths into the cosine value of the angle between them. Now we know the cos 0 gives us the highest value of cos. So if the two vectors are in the same direction, we have the highest value. And as the vectors grow apart from each other, the value of their dot product decreases. And if the angle increases beyond 90 degrees on either side, then the value becomes negative. From this, we can see that if two vectors are closer together, they have a higher value for their dot product, which basically means they have a higher cosine value. And this relationship is known as the cosine similarity. Now I'm going to show you something that will demonstrate how we can use this concept of cosine similarity in interesting ways. Before I do that, however, I would like you to keep in mind that this is a very simplified version of the concept, but it will nevertheless show you the importance of vectors. Alright, so I'm going to search for a generic sentence in Google. Doesn't matter what the sentence is, just something generic. As you can see, Google suggested me a few other sentences which are similar to what I search, but not exactly the same. Now, how did Google understand that these are similar sentences? So I'm going to write all of the sentences here. This was our original sentence. These two sentences we got as suggestions, and let's write an unrelated sentence. Now, for simplicity, let's just assume there are no more words in the world other than the ones that appear in these sentences. So we have our vocabulary, all the words that you will find in these four sentences. Now we are going to define a few vectors. So these vectors are basically the count of each word. In the first sentence, we have one occurrence of the word is. So we have a 1 here. We don't have any what, so 0. We have 1 this, so we have a 1 here, and so on. Similarly, if we write the vectors of all the other sentences, we get all of this. Now, if we take the dot product of the last 3 sentences with the first one, we'll get a value of 4 with the first 2 and a value of 1 with the last one. Now look at that. This is a very clear indication that the second and third sentences are much more closer to the first sentence or much more similar to the first sentence than the fourth one is, because they have a much higher cosine similarity than the fourth one. You gotta say, this is kind of interesting how very simple concepts can be used in real life scenarios. Now obviously, in text mining we don't use exactly this because this is very simplified, but I hope you are getting the idea. Anyway, we are almost done for today. In the next class, we are going to talk about linear combinations. Until then, take care of yourself and thank you.